The board's now populated, and as you can see, there's the isolated converter, and this is taking 48 volts input. So another e-waste find was a brick that I had pulled out e-waste, and so it takes the 48 volts in and then converts it into 15 volts on the output, isolated. Decoupling caps. On this side, we have our high voltage dividers and our MOSFET driver for driving the clamping MOSFET, and a couple of pairs of sockets to plug into the control board. So this goes on to the back of this. So this is the board that I'd done earlier, and this has a DS PIC on it, 15 to 5 volt converter, and you know, it's pretty simple. Has an E squared on there as well for retaining the set points for clamping and release. So this just goes on. Now I had whipped up this enclosure fairly quickly. Make sure everything. So the encoder was removed from the design, and now all the control is done through 3 buttons. So there's an entry to get into the program mode, an up and a down, and by holding the button for a period of time, it either terminates or programs the set points, and versus it also increments or decrements quicker depending on whether you're holding the button for a period of time. It's just easier to do it that way than wasting an optical encoder. And that goes on to the backing plate. So this backing plate is going to be mounted to the heatsink that has all the rest of the components mounted on it for the power resistors and the MOSFETs. And it certainly went together easier before. There we go. Now the tolerances on the print are pretty tight, so that's why it was a little bit harder to put together. So on the back, we've got another header that has the high voltage sense input and the MOSFET driver output, and that's going to get attached to the main assembly that I'm going to show a little later. Right, so that's our first part done. So the next part will be attaching it onto the main heatsink. Now the clamp has all been assembled, and I've set up a test to verify that the clamping mechanism clamps and then releases as expected. I wanted to have something a little bit more challenging than just raising a power supply very slowly. So what I rigged up was a capacitor bank sitting at an elevated voltage. I think it's like 18.5 millifarads, so about 18,000 or 18,500 microfarads of capacitance. And this is on the or separated from my clamp with a switch. So when I go through that switch, all that energy that's in that cap bank, so that energy is represented by the difference between what my bus voltage is, which is 21 volts, and what the cap bank is, which is close to 40 volts. So I'm just going to go ahead and just trigger this quickly. So you can see that the clamp clamped the value and then released at the 25 volts. So because my supply is separated from the clamping board with a diode, it will not discharge that 25 volts that it stopped at very quickly. So it's a very, very slow discharge. So this just shows that you can make an active clamp pretty quickly. It really needs to be tuned to what sort of load you're planning to sink into it, because the resistors need to be sized to ensure that the voltage rise that you're looking for won't exceed what you're expecting, and that's really driven by how much current is being driven into the clamp. So to set my values, I removed the optical encoder, as I mentioned earlier, because I didn't want to waste it on this project. I think it's better used on something else. So I went to a simple menu system with 3 buttons. So I can enter program mode very easily by just pushing my program mode button. And then I have up and down buttons, which I can, just by holding it, change how fast I up my set point or decrease my set point. So in this case I've gone to 10, so if I push that again I'll go to 40 volts. If I push it and hold it again and it changes color, then I can just increment by 0.1 volt. And then for the release voltage I can do that, actually the same thing, where if I hold it I can go up by tens. So that's actually pretty good. And then if I just hit the menu button one more time, now that value has been programmed into the E squared, so it'll be remembered on the next power up. So in this case, I've raised the voltage to 40.5 volts roughly, and a release of 35. So what happens when you do this again? So we did trigger, but because the voltages are so close to what our clamping voltage is, there isn't much of a rise. So that kind of concludes this part of it. I'm just going to go over a bit of a summary of what I've learned with the bits, and also the candle software for the the 0Z calibration map, which was very problematic for me.
For the final thoughts, this has been quite a learning experience to learn how to mill the PCBs. So some of the things that I learned was that the candle software does have a few bugs in it, and so the version that I'm using is 1.1.7, and I haven't checked to see if there's a newer version, but this particular version, when you're doing the height map calibration, seems to have an issue with retaining the last Z height value which affects the map when it gets applied. So what I found that corrected this problem was that once the height map had finished calibrating, before it was applied to the file, if you did a Z calibration, height calibration at the center location of your board, or wherever your first 0 point of your or Z calibration point was done, that would fix the problem, and you would get a reliable Z height correction across the board file. So once that was cleaned up, everything worked fine. The second thing that I ran into as a problem was that not all V-bits were created equal. So the manufacturer's V-bits that you could buy, Gemiscu, they were listed as having 30-degree angle with a 0.1 millimeter tip width. In reality, that was not the case. I don't think I had any of their V-bits that actually were 0.1 millimeter. And when I took a microscope and actually examined the tips themselves, you could actually see that very clearly, as shown in the pictures I'm showing. Buying a different manufacturer's V-bits actually got a lot better results, and they were much more consistent with a 0.1 millimeter bit. A second type was that I've tried was a fluted spiral bit, and the particular one I had, I actually got the wrong one in. I wanted the 30 degree one, and what I ended up with was the 60 degree one, but it still worked fine. I did the power isolation board with the MOSFET driver with that 60 degree bit, and there wasn't any major issues. But then again, I was also not trying to do fine pitch milling. So it does have its advantages, because if you're looking for fairly wide cuts without going too far into your board or having to do too many passes, then this works out well. So if you're doing any high voltage work, you'll just get a quicker board without deep cuts into the FR4. So I'm going to be ordering another set of bits that are the fluted spiral bits. That is a 30 degree bit, and I'm going to give this another try on a different board to see what sort of improvement there is. But as for using the V bits from Gemiscu, I wouldn't recommend them. I'd just stay away from them. So yeah, that sort of ends my first foray into doing PCB milling. Sort of the next steps will be to start working on an actual e-bike controller and going through that process. So some of that's going to be related to choosing a proper controller for the main control of the board, and then selecting FETs, caps, etc. And I'll be going through that in other future videos.